our particular focus today is the challenge of downhole fish and the impact that they bring on the operation of the well. The presentation will concentrate on three main areas. Firstly, what are the causes of downhole fish? And especially, what is the significance of this at $40 oil? And when I started writing these slide notes, it was $30 oil, but things have changed a little bit since then for the better. But still, it has a significant impact in today's environment. We'll also then introduce a concept that we call visual analytics and how we use this technique of quantified vision to help overcome a number of different challenges. And we'll look at some of the technologies that support this and the overall technique behind it. But to really demonstrate the effect of that, we'll look at how we apply that service to the challenge of fishing and case studies of operations we've been involved with in helping to remove these problems quickly. So just to get us started, what is visual analytics? Well, put simply, it means quantified vision. And by mapping the way the overall optical system manipulates captured rays of light, we've been able to calculate a transform function that restores the true geometry of what we're seeing in the well through the camera back to its original size and shape. And by doing that, it enables us to take highly accurate measurements of any features or anomalies that we see in real time, right there and then at the well site. This helps us to not only understand the root cause of the problem, but also understand the severity and impact that this may have. And that knowledge helps improve our decision making and gets us to more decisive and more effective action sooner. The first example showed some hydrates that are formed in a well, and the second example, looking sideways at the pipe wall, shows us some small corrosion events that are occurring. And again, by knowing exactly the size, the shape, the location, the number of them, their orientation relative to high side, proximity to sidewall, and even how they're changing over time, we can get a very detailed picture of what's happening inside the well that we can use to help improve our decision making and make sure that we choose the right option first time to overcome the problem. Now, this could be monitoring corrosion and the rate of change of well integrity. But for our example today, we're going to concentrate on fishing and that downward view that we saw first of all. Now, there are a number of applications that we could apply this technique to, and you can see a number of them here on the slide that we've got up now. Everything from looking at the function and performance of complex completion items, valves, sliding sleeves, anything with an unusual shape and a moving performance. We can also look at things like restrictions in the well. We can look at perforations and sand control performance, but it's really here today where we're looking at downhole fish that we're going to spend our time and our attention. But before we go there, and before we start to look at the case studies, I wanted to really examine the impact of fish. And to do that, I wanted to look at some overall figures that I've gathered from the industry about production and its efficiency. The concept that you don't get something for nothing is universally accepted, and it applies to pretty much everything in life. And you can certainly see evidence of this within the oil and gas industry. It's a fact that all wells experience production decline as reserves are depleted from the reservoir. And it's a fact that you have to act to maintain production, not just to increase it. And one of the most direct means of renewing this production is the drilling of new wells. And whether you're commissioning a new field or whether you're infill drilling an existing field, you're effectively adding fresh production to compensate for the decline of the existing wells. But if you ask any driller, they'll tell you that in the event of an economic change in environment, it's drilling that gets hit hardest. And if we take a historical look at the view of the oil price over time, and in this case, I've plotted West Texas Intermediate. I could have put up any other index, but they're all very similar in their shape. And if we compare that to the number of active drilling rigs, you can see there's a very close correlation between the two. The two track each other extremely well. But what I'm interested in is seeing what happened in the events after 2014, when we had a very large change in economic environment. And to do that, I'll put up a second plot that looks at the relative change in both oil price, shown in orange or in gold, and the rig count, shown in blue. And what I've done is I've used the 2014 value and said that was 100%, and we'll track all changes relative to that point. And you can see just how closely the rig count and the oil price have changed over time. They're within 10% of each other for the most part. But that isn't the whole story, and that paints a very negative picture, but actually there's a lot more positives in here. If we replace the price of oil with our overall production, we get a slightly different view. You can still see the rig count and distribution over the different geographic areas, but you'll notice here that other than for very recent events, overall, our production levels have been increasing over time. But at the same time, the rig count has declined. Again, if we replicate the same view I showed for the rig count versus oil price, but now replacing that with our production history, you can see that there's a very large gap now between the amount of oil that we're able to produce and the number of rigs and essentially new wells that are being brought online. And the point here is to answer the question, well, how have we achieved this? And the answer is that we've become more efficient. And we've done this in a number of different ways around the world. But to begin with, I want to consider from the drilling aspect how we've become more efficient in delivering new wells. And if we consider that majority of these new wells have come in the Americas and from unconventional resources, we can explain some of what we're seeing here through the step change in rig design that's come into effect during this time, that have brought in fit for function horizontal drilling rigs with longer laterals and more fractured stages. Operators have also adopted the pad drilling approach instead of standalone wells. And all of these factors have combined to create wells that are longer, that produce better, and have a lower associated drilling time. So it's fantastic in terms of overall well efficiency. But the twist here is that these wells have become much more complex, and as a result of that complexity, much more susceptible to risk. And again, thinking about the unconventional wells in particular, frac hits are a major issue that's arguably compounded by some of these factors. The longer wells, their closer density together of the laterals, it means that there's much more interactions within wells. You're also putting more plug and perf assemblies in there and making more trips in and out of the well. So with all of these variables in play, when things go wrong at this early stage in well delivery, understanding the root cause plays a massive part in getting the operation back on track and getting it back on track quickly. And it's here that we'll look at our first case study in addressing this problem in unconventional resources. The video that we're going to show was first published as one of our regular video of the months, and it comes from a well in Argentina. Again, an unconventional resource that was being delivered and brought, hopefully, onto production. We're going to join the story quite towards the end of the well's delivery. And in fact, the operator was partially the way through removing all of the stage plugs post completing the frac and prior to bringing the well online. But midway through this process, halfway along the lateral, they encountered a restriction, most likely deformed casing as a result of a frac hit. They tried to mill through it, but became stuck, and ultimately they left the mill behind midway through the lateral. We got involved to run our Optis M125 memory camera deployed on coiled tubing to try and understand what was going on. And the images and the measurements that we'd provide would give detailed information about the status and geometry of the fish. The results showed some ovalization of the liner, but ultimately, when we came to find the fish itself, we could see that it was sitting on the low side of the well, as shown by this high side indicator and the presence of the gas cap on top of the liquid. We then started to take measurements of this to understand the proximity of the fish to the pipe wall and the access that we had around it that would be used then to tailor an overshot. That information allowed the operator to make modifications to the standard overshots that they had And they were able to then deploy that on the next run-in hole with a fit-for-purpose design tailored to the exact fish geometry. The good news is that fish was recovered on the very first attempt. After that, they chose a slightly different mill for the remainder of the operation and removed all of the plugs successfully, bringing the well back onto production with a minimum delay and hopefully a well that will continue to produce as planned for its life. So overall, a great story in getting back on track and getting back on track quickly. But to really put that into context, I wanted to explore the value in recovering that fish and why in particular we should care so much about efficiency and particularly time efficiency. So to answer that, let's have a little look at the production profile for a typical unconventional well. And here I'm using data from the US Energy Administration and from the Eagleford shale plays. On the left-hand chart, you can see the expected cumulative production versus time. Now, the orange line is what the normal well would produce. And given that the fish was located halfway along the lateral, if we plug that off and just produce from the top half, then I've drawn the black line showing roughly what we'd expect at 50% of the production. Now, if we then convert that into a monetary value at $40 barrel prices, we can take a look at a few key points in time. And I've plotted a number of them here, but really the ones to look at most of all are the 5-year values, because this is where 75% of the production has actually occurred. So most of the productions here, this is when really the, if you like, the cream or the most profitable parts of the well have been used up. And you can see at this point, there's roughly an $11 million revenue difference between these two scenarios, one with the fish in and one with the fish recovered. But the other important factor is at the other end of the spectrum at this 0.25 quarter of a year or 90-day value. And this is a particular performance indicator that most operators look at, because it's around this time that a typical well will start to pay back the cost of drilling and completion. But if we look at the well with the fish in it, it takes almost a year to get to a similar value. So that cash flow, that return on investment is much slower, which puts a lot greater strain on the performance of the company and their ability to invest in future wells. And just to highlight that further, that time efficiency is really key because of the way these wells produce. So if we take a look now at the production rates versus time, you can start to understand this in a great bit more detail. As you can see here, we've plotted now the production rate versus time on this chart. And you can see initially there's quite high production, but it tails off extremely quickly with the pressures involved. And at the 1 year point, we're down to roughly 25% of the original production rate. You can see again, we've drawn the black curve showing the reduction in this because of the presence of that fish. So let's take that forward. And given that our fish occurred even before the well was put online, we're talking about delaying production at its absolute peak. So if we take a look at our scenarios versus time and assume a linear production rate for the first 15 days, as I've plotted here, we can show really the value of getting back on track quickly. The orange curve shows the way our operation in this story panned out, that the fish occurred, the camera was mobilized on day 1. At the same time, the operator was starting to clean up the well, getting ready for the camera to be run. On day 2, the camera survey was performed, the information was delivered, the OVERSHOT was being modified, ready to be run on day 3. And at that point, the fish was successfully recovered and the operator was able to continue with their usual plan from there on. But the black curve shows what would happen if we extrapolated over time, delays in getting that fish out of hole. Now, you'll have to decide amongst yourselves and for your particular circumstance, what a typical fishing operation looks like. But it's key to note that every day of deferred production costs that operator roughly $65,000. So compounding that day on day, it becomes a very costly exercise. And what we've demonstrated, and we have a number of case studies like this, is that bringing these wells back into operation quickly has a massive benefit, and that FishVA has proven to be a very effective enabler in bringing that about and helping people get back on track with their operations. So just to make that relevant for the rest of the world, we've talked about efficiencies with new wells and new well delivery, and essentially the unconventional sphere. But for other markets, and in particular places where I operate, the North Sea, for example, they've gone about the efficiency challenge in a slightly different way. For one aspect, we've looked at increasing our production through enhanced oil recovery techniques, delivering more barrels from the same wells. But perhaps one of the most cost-effective strategies is through the addition of incremental production via intervention. And to illustrate this point, I'm going to use data from my native region, from the North Sea, and for production from UK waters. Now, after the economic downturn in 2014, the whole of the UK sector took a very deep and meaningful breath and looked at how it could get back into shape to compete at sub $50 oil. The resulting strategy recognized the need to keep drilling, but it also identified some low-hanging fruit that could be extracted from existing wells. And one of those was the reactivation of wells that were shut in. And at that time, they identified nearly 650 wells that were shut in, but could be brought back into operation. And that was a quite large percentage of the overall, what I'd call active well stock. In other words, wells that weren't already abandoned or had been made ready for abandonment. These are wells that, in theory, could be brought back into production. But when the Oil and Gas Authority looked at the causes of most of these shut-ins, they actually found some pretty good news. That other for a few limited factors like formation damage and facilities limitation, the other, well, close to 97% or 95% rather, were for issues that we could potentially address. A large amount due to well integrity, a large amount actually due to wellbore fish and maybe other completion components that weren't functional, a lot of water production, some sand, artificial lift issues. But again, all of these things could be challenged, could be overcome through remediation and intervention. And with that, the UK started to look at the best candidates for intervention and set about chasing barrels by doing so. A year later, the Oil and Gas Authority published a report on the success of some of these activities. And what they showed was that they'd been able to deliver roughly 44 million barrels of incremental production per annum as a result of these activities. Some of that was through safeguarding interventions, mainly pumping and stimulation work. But a large amount of it was from this well restoration activities that we've just looked at. And we can break that down into a little bit more detail with the subsequent slide that comes with it. This shows that same breakdown of the overall issues, but underneath that, they've put a plot of the incremental production gained by each of these types of interventions. And the blue curve is the cost per barrel for this intervention. So what they've recovered in a year, they then divided it by the cost of those interventions to show which was the most cost effective. And you can see that some things were extremely easy to do and very good return on investment, like tree and wellhead repairs, safety valve reactivation, gas lift repairs. But the point I wanted to draw on this one is the relatively high cost of recovering fish. Now, these were for wells that already had fish in them and could be planned up front. But even then, it was costing them close to $40 per barrel gained. So the net increment is relatively small compared to the value of the production. But what we're going to talk about is how we can drive that cost down by making these operations more efficient and more effective in exactly the same way we did in the first case study. And on top of that, it's also worth remembering that any of these trips in hole for any of the other activities could result in a fish at any time through misfortune or an unfortunate sequence of events. So again, even in this environment, when you're not necessarily expecting a fish, being able to react and deal with it effectively plays a big part in the economic argument. And to demonstrate that, we'll look at our second case study. And this actually comes from Southeast Asia. And although we looked at data from the UK to begin with, the challenge out there in Southeast Asia is very similar. Quite a similar environment, offshore platforms, aging assets and installations, trying to get them to last longer and produce beyond their existing lifespan. But this particular field is located in Malaysia and originally completed in 1991. But sadly, very early on in the well's life, there was a problem with the subsurface safety valve, and they tried to remediate that with the installation of a wireline retrievable subsurface safety valve. Unfortunately, it's safe to say that didn't quite go to plan, and 3 separate fish were created as a result, and in the end, the operator shut in the well and suspended it. Over time, that original operator tried 4 attempts to fish those assemblies. Unfortunately, each of those unsuccessful. But in 2014, the asset was actually sold as part of an asset transfer, and the new operator looked at the potential underlying value of that early production that had been shut in and thought, well, let's have one more go at fishing this before we then default back to a workover. And to do that, they employed EV services, and again, using memory cameras deployed on slickline to try and help them every step of the way to understand what exactly they were dealing with and advise how best to overcome it. The results were fantastic, and it makes for a very good case study. But when we came to the key part of the video, we came to look at the very top fish that was left in the well, there was quite a surprise, because what was expected to have been seen was quite different to what we saw in reality. And the key thing here was that the fish neck was quite different to that we're expecting to see. It had a much shorter fish neck than was originally anticipated. And with that information, the operator modified an overshot to reduce the catch length. And having performed that, they were able to recover that fish first time again. So having identified what the issue was for all those other operations, and with that extra knowledge, they were able to get going. That helped them remove the slip block plug that was at the top of the well. Then they could get onto the bulldog plug that was located below it, and then ultimately remove the problematic wireline retrievable subsurface safety valve that had caused the initial issue. They then went on to install a new wireline retrievable subsurface safety valve successfully this time, and bring the well back online. Restored access, got production going again, and they were able to deliver over 1,300 barrels of oil water-free on initial production. So a fantastic story there and a great outcome for the operator involved. And again, this was part of an SPE paper that we published, and you can see the number up here if you want to see the details of this and other operations that were very, very similar to this in the same region. But again, if we round this out by looking at the economic impact of this and what it meant for the operator, well, firstly, by getting the well back online through rigless intervention, they saved over $7 million by avoiding bringing in a jackup rig and having to perform a workover in that sense. So from the cost-saving point of view, fantastic. But if we then look at this as an annualized production value, and assuming that the production doesn't decline too significantly in that first year, that 1,300 barrels of oil is worth roughly $18 million in production, even at today's $40 value. So you can see there, that's a swing in fortunes of nearly $25 million for this operator. And again, we've got lots more case studies very much like this of bringing idle wells or shut-in wells back online through video-led interventions. And just to round off on the case study section, I actually spoke with a friend, and someone I've worked with for a number of years, who is a senior advisor across a multinational operator. And his view on the success rate and the enablers of getting fish out of hole is you've really got to know what you're dealing with. And in his words, half the job is knowing exactly what's happening in the well with the fish, what it's doing, where it's located, whether it's stuck, whether it's free. With that, combined with your knowledge of what has worked in the past for getting fish out in those scenarios, you've got half the battle won. So again, know what you're dealing with, generate a plan and strategy to suit, and you're in a much better position to hopefully overcome and move forward in a time-efficient, cost-effective manner. Okay, so at this point, we're just going to take a little break. I'm just going to bring up here the overall chat window that we've got set up for the call, because Mike mentioned that he was going to put up a couple of polls as we went through. So I just wanted to share that with you, make sure everybody's seen it, give you the opportunity to take a little look at that, and maybe answer some of the questions that are here. So if you notice on my screen, you can use the little command prompt here to bring up the chat channel. And in there, we should have the questions that we've asked. Again, just multiple choice. You can just select your answer and click submit vote, and away we go. So I'll give you a few more minutes to do that whilst we're rounding out the last parts of the technical session, and then we'll take a look at some of the results at the end of this call.
Yeah, thanks for that, Tobben. I just want to mention it looks like around 10% of you have answered already. But if you can't answer the poll for any reason, could you let us know, and we can see if we can have some sort of a workaround there. So thanks, guys.
Okay, so just to wrap up, we've looked at the gains and efficiency you can get through information and really that downhole intelligence that you can get by using the video systems. But I also wanted to share with you some extra steps that we're taking and that we've brought to the market that can increase this efficiency even further. And that's to do with the way we can gather that data in the first place. So what we're showing here in this first example is what we call video whilst fishing. And in this case, we've taken a standard Boeing 150 series overshot, and we've created a little bit of extra space in there to fit one of our memory video cameras in. This is a great combination potentially then for coiled tubing fishing operations, that in the event that the fish is recovered first time, then there's no change in plan. The modifications we've made to the overshot make no change to its physical strength and load bearing capabilities. But what we've done by burying the video system in there is that for whatever reason, if you're not able to get the fish on your first attempt, you can download the video and start to understand what the issue is. Perhaps the fish isn't exactly what you thought it was, as we saw in the previous example, or perhaps its orientation and geometry just isn't right for the tool that you're trying to use. So with that insight, after one run in hole, hopefully you can adjust your strategy and move to a more successful outcome. The second example of, again, video whilst fishing, as we call it, is the simple addition of a magnetic shroud. And here you can see our regular camera system deployed within the shroud, which has a very powerful rare earth magnet placed on the front face of it. And you can see here it's very strong. It will pick up to 20 kilograms in weight, or 44 pounds. And it's really designed to help get out small components, things like maybe broken assemblies, slips or dogs that have become removed as you've either tried to install or recover completion components. But again, these small items, you wouldn't be able to tell if you have them on a regular baler run. There'd be no weight indication on there. And even a regular magnetic run, you wouldn't be able to tell how many fragments and pieces there were, where they were, and more crucially, had you successfully recovered them all. But by having this with the video at the same time, we can approach the area of interest, we can see the objects, we can count their number, how many are there, and we can also verify that we've picked them up in one pass. And as you can see here, as we get towards the bottom of our test chamber, you can see the washers and small fragments that we've placed there. You can even see the metal filings start to fly up towards the magnet. And again, we can watch as we pick them all up. And crucially, we can also track them as we come out of hole. If, for example, we go through a restriction and we end up dislodging one of these items, we'll know about it. And we can go back and pick it up and find where it was in that same run. So minimizing the number of trips in hole. The second example is a slightly larger object, but you'll all recognize this. And please don't go dropping spanners in wells, but it seems to be the default test for these types of things. But again, we get closer to this double-ended spanner, and you can see that it starts to move as the magnet engages it, and ultimately it becomes affixed to the front of the camera and magnet system. Again, we'll track that out as we pull out of hole, make sure we don't drop it, and if we do, we can go back and collect it. So again, not just the fact that we can take measurements and that we can see what we're doing, but also that while fishing video enabler, make sure that we can do this in a minimum number of trips, and ultimately we can get to that keyhole surgery position of knowing what we're doing and changing our strategy in real time.
Tobin, we've got two quick questions here. First one from Tommaso. Can the video tool work in high pressure, high temperature wells?
Yes, that's a great question. And we have video systems that go up to 200 degrees Celsius. They are time limited because we've put them into a thermally isolating flask. But we use those extensively for HPHT operations in the oil and gas environment, but also actually a lot of the time in geothermal applications where the well temperatures are way above what we normally expect in the hydrocarbon industry. So we have those variants available in real time up to 200 Celsius and up to 160 degrees Celsius in memory mode at the moment. And we expect that we'll push that envelope further as we go on. And the pressure rating is actually not such a big deal. We have camera systems that we've adapted for deep water applications that will go up to slightly above 20,000 PSI. So again, there's no real limitations on the physical nature. It's more about the temperatures. But up to 200 Celsius, yeah, we've got most applications covered at that point.
Okay, and the second question from F. Young, how far down from the camera location on the coiled tubing can it see?
Oh, that is a good question. And you've caught me a little bit off guard there. I'd have to check the length of the overshot that's below. But to be honest, the main issue in how far we can see is more to do with the well fluids and how clear the environment is. So as long as we've got a good, clear environment in the well, then we can see several feet, even meters further down. It's to do with the amount of light that we get there, how clean the well is. So I don't think in any operations I can recall, we've been limited by that as long as we've worked on the well conditioning side of things. I'm actually joined by a number of colleagues from the EV team, and I'm just thinking, Fraser McDonald, who runs our operations out in the Middle East, you've got a great deal of experience of fishing operations. Would you like to add anything to that, Fraser?
Thanks, Tobin. I was typing in the background to F. Young's question. So yeah, as you pointed out, Tobin, the wellbore medium, whether we're in a fluid, a clear gas, or if we're in a brine, which is not so transparent, the distance of the focal distance of the camera is dependent on that. But from my experience, when we're in a clear gas environment or a very, very clear transparent water, fresh water, for example, the camera can certainly see, up to about 6 feet, depending on the ID of the well and the light reflection if we are approaching something with a metallic surface. So generally, we would certainly see very clearly within the 3 feet down to the 6 inches, but we can capture that. So.
Okay, very good. Well, we can probably come on to that question in a bit more detail, but I hope that that helped. If not, speak up, type another note. We'll try and address it. But the good news is really that's pretty much it for today's session. And really, just before we open the floor up to more Q&A, I just wanted to summarize by saying that this application of visual data analytics, it's really transformed the way we use downhole video. We're now able to get so much more data in a very compact way with this measurement capability thrown in, that this has led to a real expansion of the number of applications that we can use this technique for. And I hope that we've shown through the case studies and discussion today that we can apply that technique to really help optimize the efficiency and effectiveness of downhole fishing operations. And if this is something that you're perhaps faced with at the moment, if this is one of those things keeping you awake at night with the wells that you have, then we're here to help. We'd love to help discuss that and see if we can advise and guide a way of increasing your chance of success. So with that, I'll wrap up and we'll hand back for questions. But just before I do so, a little reminder again that the SBE paper that we looked at, the number of that is just provided here for reference. And if you don't manage to get a question in today, but there's still something you want to discuss, then actually one of the best ways of getting in contact with us is to go to EV's webpage, evcam.com. And if I just bring that up on screen now, you'll see on the very home page, if you scroll down a little bit, you'll get the contact details of the EV salesperson closest to you in your region. So I'm here in Aberdeen, and I get the lovely Michael Emsley as my local sales contact. But this will change depending where you are, and it will give you a number for the most closely directed person in your area. And all of the team here at EV are very experienced. They've got a lot of knowledge. So it's a great way of getting in contact and hopefully getting some advice on moving forward. But with that, I'll hand back to Mike and to Fraser to help me guide you through the questions and answers section. Okay, thank you.
Thanks, Tobben. Yeah, we've got a couple of questions here about the. Firstly, is there any options for cleaning the camera lens in hole? For example, after going through a wellhead with lots of grease. And another question from Ahmed, do we need to shut in the well to get this kind of quality video?
I can help with those questions, Tobben and Mike. Perfect. Tobben is bringing up a very good slide with regards to the contamination of a camera. Tobben, you wanting to take through it? You have the slide. How would you like?
Sure. Okay, Fred. I'll go through what I have here, and maybe you can add to that and pick up what I've missed. But no, it's a great question. I think that the biggest issue that we face with cameras is maintaining that optically clear environment. It's the one thing that we have to rely on. And really, the first few 100 feet inside the well is probably our most problematic, especially on wireline interventions where there could be a lot of grease used to help lubricate and maintain pressure. So a really simple way to get around this that we adopt is we use what we call soluble covers. These are polymer bags that have a chemical composition that dissolves on contact with water. And we have them made at different grades so that they will decompose at varying temperatures, which allows us to get a certain distance into the well before they start to degrade and come off. So what we've got here, this is what they look like. And if I apply them then to a tool in test environment, we've got our downward viewing camera on the left with the cover on it, dipped into some wireline grease. We then pour some warm water over that with a kettle, and you can see that the polymer cover completely dissolves, and it takes with it that wireline grease that was covering the lens and the rest of the assembly. Similarly, we do the same with the side view camera. We cover that with the cover. We then introduce some warm water. It washes away, and it takes with it the coverings that we have on the lens. And finally, on the right-hand side, we've actually got some footage of this occurring in real time in a real well. The video is a bit blurry to begin with because we're looking through that cover. But as we start to move into the well, the temperature is starting to increase, the cover is starting to become more pliable, it's starting to dissolve, and we can now start to see through it. And what we'll do is we'll keep running in whole until we're happy this is soft enough. We'll put on the brakes and the cover will start to disintegrate and come away from the lens, leaving the viewport perfectly clear, taking away any solids and debris from it. And if we carried on with the video beyond this point, just a few more minutes, that cover would have dissolved completely, leaving nothing behind inside the well, no restrictions, no extra objects, and we would just carry on with the operation as normal. So Fraser, anything to add to that?
I think you covered it perfectly there, Tobin. Yeah, thanks.
Great, thanks, Fraser. And I think the second part of the question was about what can we do to clean up the lens down hole. And again, it's another great question. And the way I'll answer that is to say that actually the presence of oil inside the well is not necessarily an issue for us. As long as we've got some sort of clear medium in there at the area of interest, whether it's a gas cap or a water column, and we could potentially manipulate the height of those with some applied pressure at surface, or we could bullhead, or in this case, you could even rely on the clarity of the produced water or gas. But if there is oil, it's not an issue. This video clip we're showing now is us going through the undulations of a horizontal well on coiled tubing. And you can see that we go through the oil column and either out into the free gas or back down into the produced water. And once we get past the oil column itself, the special coatings and surfactants that we put on the lens mean that that oil will wash away very, very quickly and get back to a clear image. And in the worst case, if you have got a particularly stubborn blob of something on the lens, you can simply reciprocate the wire or the coil inside the water, and hopefully that will wash the lens clean after a few attempts. And that's something that we build into our processes and our planning, and the expertise of our engineers on site will be able to guide you through and get these images in the way that we require. So again, Fraser, with all the operations you've been in, is there anything you want to add from your experience in that respect?
So yeah, Tobin, the main thing is obviously is the well preparation and the information that we get to plan our camera operations. It's vitally important that we EV understand what's in that well, what's in your well, and how to go about the suitability for running a camera in it, whether we go straight in, whether the well is shut in. We had a question there from Azikri regarding, do we need to shut the well in? That's a good question, and it depends on what you have in the well at the time. For example, if you are in a high water cut, you have an oil producing with a high water cut, you know, roughly around about 80% plus of water production, then of course you can shut the well in, allow that time for the oil and produced water to separate, and then you would deploy the camera to the depth of interest and be in that clear produced water. And as Tobin showed on the video there, when we go through the oil column, there is no contamination on our lenses when running through oil due to our unique lens designs, our sapphire lens designs, and the surfactant that we apply to our camera lenses. So yeah, that was one point, Tobin. There is a few other questions on the chat window. One regarding the well preparation. The slide you just had, Tobin, with the NTU level, I think that's probably a good one just to answer one of the questions, is the quality of the fluid that we're running in, which is a very common question that we're asked. And as you can see on the slide, I don't know if you want to talk through the slide, Tobin, or leave myself.
Go ahead, Fraser. You're there now.
Okay. I'm here. I'm prepped. So here you can see there's a sample on your left beaker with water, and that is an NTU level of 1.6. You can see that there's a couple of coins dropped in there, and we can see the coins very clearly whilst looking through that fluid. On the other hand, you have cola, which is also a very low NTU level. However, the light levels that cannot transfer through there because of the opaqueness of the fluid would be very difficult for anything to see through that. So on the chart we have on the right, the six chart levels, we can see the different NTU levels of the fluid that we're in a test pipe here. Obviously at 0 to 1 NTU, very, very clear. We can see the detailed on the test chart. And as we come up through the levels of the NTU, it becomes very difficult for the camera to see. So this is exactly why we at EV need to know or to understand the type of fluid and the level of NTU that you have in the wellbore. And that allows us to produce the correct recommended running procedure, the wellbore cleanup if applicable, and the well-specific running procedure itself. So that's our gauge, our chart for how a camera can see in a well, and the type of fluid that we ideally would like to be looking at. So keeping the NTU level as low as possible, 10 and below is a really good target, and that would give you the clear images that we've seen in some of the case studies. There's a question here from Tommaso. Hi, Tommaso. Asking, can we use the camera in combining with tractors, strokers, and fishing nets? So the first question, well, to tractors, yes, we can certainly run on tractors. We even have our video well structuring capability, where you can actually live see as you tractor as we approach it with certain tractor providers. Strokers and fishing nets. Tobben showed a slide earlier on the overshot where we're actually inside the overshot with the camera. This is sort of a video whilst fishing application. For strokers though, we have not. I don't believe we have any history where we're actually at the end of the fishing net, where we're actually in the fishing tool, other than the overshot that we're using. So. But certainly for tractors, we can run down in combination with them.
Yeah, indeed, Fraser. And we have tested with a number of tractor providers that capability to be on the end of the payload for the mechanical services. I haven't got an example that I can show you of some of this, but one of the applications we use with a real-time combination of tractor and mechanical assemblies is the locking open of safety valves and other sliding sleeve and valve assemblies. In some cases, older designs, it's quite difficult to lock them out with mechanical interventions. And what the tractor combination allows you to do is physically deform the sleeve into position, so you can permanently lock it in whichever position you want, open or closed. And usually for safety valves, it's for locking them open so you can install something else. Now, the beauty of what we've been doing is we have the video combined with that system in real time. So we'll go in with the video to begin with. We'll take a look at the flow tube and flapper assemblies and make sure that they're in the condition that we want. The wireline tractor company will then engage their system, and they will deform the flow tube into position. We'll then come back and take a look at the success of that by placing the camera right on top of the flow tube and have the operator activate the control line. And what we'll normally see is a very, very small amount of movement if the valve has been locked effectively. But if it's not, then you'll see the flow tube start to move in its normal fashion. So with that, we've got, again, this keyhole surgery approach. Look at the area of interest, perform the operation, and verify success at a single trip. And the same could be applied in theory and principle, because it's the same technology, to doing things like sliding sleeve manipulations, opening and closing those and verifying that they're in the correct position. And although we haven't shown it here today, we have a technology that has a 360-degree field of vision. And we've developed with a partner a very specialized version of that for coiled tubing applications. And that's exactly the type of thing that is designed to use. So again, see the problem, perform your operation, confirm success in real time. Okay, any other questions that have come to light? Either Fraser or Mike, anything else we should pick here? There's lots of questions I can see.
There certainly is. I just maybe skipped past one accidentally. Sorry, Roger Solo. I missed your question, but I'll answer it now. And your question is, what approach what recommended approach for retrieval of a surface-controlled sub-safety valve dropped close to the XN nipple around about 6,500 feet in a vertical well? Well, it's possibly biased, my recommendation, but that would certainly be to help you understand how that fish is located, where it's located, is it stuck, is it free, which is going back to some of the slides that Tobben mentioned, and that would certainly be to run a downhole camera to give you and the fishing team the information that's required to successfully retrieving that safety valve downhole. So that would be my approach if I was to inspect that Mojisolo. So thanks for your question. I hope it's an agreed answer that you have to. I'll let you go back, Mike, if there's anything else, or Tobin.
Yeah, and just to add to that response, Roger Solo, if this is a particular well that you have an issue with, again, reach out to your local EV representative. They can take a look at this with you on paper and try and come up with a plan of action that may be able to assist there. And again, there's no obligation, but if you like what you see and we can help guide you through it, then perhaps that'll save a few sleepless nights from your side. And also just below that, there's a question from Frederick. Thanks for joining us again. I recognize your name from previous webinars we've been on. And you asked whether the side viewing camera is available if you have the magnet shroud. I believe we can do that. And designs we've put into effect mean that we can shroud the front portion of the camera, place the magnet on it. And for light load bearing activities, that's okay. Lifting up small fragments, we can still have the motorized side view camera, or potentially, as we go forward, this 360-degree array camera. But again, if this is a particular problem that you're thinking about and trying to deal with, again, let's have a conversation about it and see what we can do to suit. Because one of the other real strengths of EV is that everything that we make in terms of downhole equipment, all our cameras, all the technologies, is designed and built in-house. So if we haven't got the exact solution that you need, we'll make it. And this is part of our function. We do it all the time. We make specialist assemblies, sometimes one-offs or multiple offs, but really that's what we're here to do. We're a specialist team. We can hopefully get the system that you require and the information that you need.
Yeah, I'll just add to that, Tobin. As Tobin's saying that we specialize, and the reason for the magnet camera actually came from a coiled tubing operation, a coiled tubing requirement, and that's why we developed the magnet to be attached to our shroud that covers the end of the camera. That also gave us the ability to pump and circulate. So this maybe goes on to someone else's question. I think this is Richard Young, who's just below that question, about cleaning up. So when we run coiled tubing and we can pump through a clear fluid through the coiled tubing, then that allowed us to clean up that area of interest where we were actually connecting to the fish and picking it up with the magnet. So that is why we had it in a coiled tubing application, but certainly, as Tobin says, we're very ingenuitive at EV. We can design things, customize them for a particular well. And going back to Richard, yeah, for cleaning up whilst we're in hole, there's several solutions for that, such as pump down through the kill line with a clear fluid. There's the bullheading, circulating through a coiled tubing. Also, if we are in a workover, we can run through drill pipe, and you can circulate through the drill pipe, which is just above the depth of interest, to give you a really clear environment where you may have well control issue. You cannot completely displace that fluid. You need to have your weighted brine above us. We can just clear that few feet that we just need to see to get the picture and get back to surface. So several means to do that, and we have quite a number of years of experience and expertise in wellbore cleanup.
Great, thanks, Fraser. I think there's one or two more questions there. There's one here from Kai Evans, who's joined, about creating a three-dimensional image from the video system. And Kai, it's a great point. It is something that we talk about quite regularly in technology reviews. We built our 360-degree circumferential camera exactly for that, for doing three-dimensional imaging of wells, combining either the engineering drawing of what's expected to be there and then placing the video over the top of it, or doing the same using things like multi-finger caliper data from real well surveys. We haven't applied it to the forward viewing system yet, and we use the word yet as a qualifier because we've been so successful with the spot measurements that we've made, and in most cases that's all the information the operators needed. A very, very quick decision of what does it look like, where is it, what sort of accesses have I got, and then bingo, we're off and running on the very next trip. We could do, in theory, a similar exercise of taking a drawing of an object and then superimposing the image on top of it. We just haven't really had somebody driving that application so much for us. But hopefully, if you do go onto our website, you can see some of the three-dimensional imaging that we've achieved with the circumferential camera that we call Optis Infinity, and that is a tremendous application of 3D visualization with combined measurement capabilities.
Okay, we've got another question here from Archer. Is it feasible to run a camera in the well annuli?
Good one. Yes, we get requests about this every now and again, and I think the best way of answering this is that we are quite proactive with the team that we have in engineering. If this is something that is really, really hurting your operations, let's talk about it, see what we could develop to suit. I don't think we've got anything that's exactly fit for going through a wellhead tree at the moment or anything like that. But we do have camera systems that run on umbilicals, either on drill pipe or just on tugger lines, for example, with downwards and sideways viewing systems. So adapting one of those to suit your needs may be possible. It really just depends on what size annuli you have and how you want to get that access. So I think the best thing there, Arthur, is to find somebody in your local region. If you want, you can contact myself. I'm quite easy to find with my name, and we'll have that conversation, look at your problem, and maybe come up with an engineered solution to suit, which yeah, we'd be very happy to talk about.
Okay, thanks, Tobben. And one last question here from Stuart. Are your SRO operations performed on E-line cables, or do you run on fiber?
Thanks, Stuart. Yeah, all of the examples that we've shown on this wall here, they're all in real time on standard electrical conductor cables. So that there are companies that use fiber optics, and we do as well, fiber optic enabled coiled tubing, for example. But with the video compression techniques that we use, combined with an extremely fast and stable wireline telemetry, we get very, very high quality real-time video on regular monoconductor cable. So really nothing special required. It saves a lot of time and effort at the well site having to swap drums on units. We pretty much rock up, test on the cable, and in most cases we'll run without any issue whatsoever. If it is a particularly exotic cable, and Fraser, you'll probably comment on this, we'll go with a bunch of different adapters at surface, and extra load boxes to make sure that the telemetry is in its sweet spot. But yeah, we have very, very little issue in connecting up and getting these images in real time through standard wireline equipment. Fraser, anything to add?
Just yeah, as you mentioned, our surface panels and our surface equipment is equipped with state-of-the-art software firmware, where it picks the absolute perfect connection and data uplink and downlink to the tools downhole. We set up our variables of the camera, the telemetry, and the surface panels to that cable that we're running on. So we run on various lengths, sizes, resistance, types of cable that require a tuning of that of that cable to be on our operating system. So yeah, we have a lot of experience on various different types of cables. Some can be more challenging than others, but certainly our surface equipment and our telemetries can operate with a extremely high bit rate as well, to give you that really clear, consistent frame rate and clear picture.
Great, thanks, Fraser. And really, I think we've answered most questions. There's one I've spotted here about locating a leak source, and maybe this also relates to some of the other questions we've had as well. Our website is a great repository for information. We put a lot of effort into sharing success stories and video clips with the community. So if you come onto our website and click on the case studies button at the very top, you'll then be presented with a range of different videos in this grid below, and you can extend the list in here. But as well, we've put a filter on here. So if you are interested in, okay, what can I do on wireline cables, for example, we'll have an electric line filter on here, so you can see case studies that have been acquired just on standard monoconductor cables. But also we segment these by application. And someone just checking here is Elvis has asked about leak detection. So if we quickly find our leak challenge, there's a whole heap of videos in here showing leaks. And the one that I'll just come to quickly is showing a very, very small annulus to tubing leak in a well here. You can see here on the right-hand side, gas bubbles coming out of the annulus through a leaking connection from the downward viewing camera. And this is a very, very low leak rate. It's tiny. You might be able to pick that up with an acoustic leak detection tool, but certainly seeing it and understanding the cause of the failure, the video is fantastic for that. And when we switch to the side view image, you can actually see the bubbles leaking through the connection threads here. So just a little note to say the way we're streaming this with Microsoft Teams, these videos probably aren't being shown at their greatest frame rate and resolution. But if you want to, after the event, quickly pop onto our website, take a look at the case studies, you'll see them there in their full glory. And we also have a YouTube channel where all of our videos are stored, and you can see them in full screen mode if you wish.
Got a question from Rick. Is FishVA being ran on eCoil?
Oh, great. Thanks for the question, Rick. And yes, it's a good question. Can we perform this on a number of different conveyance methods? The answer is yes. And the cameras that we've developed for real-time applications, we have versions that will work on E-line tractor in real time, and e-coil through electrically enabled coil, as we call it, and also fiber optic enabled coil tubing. So there aren't really any limitations on delivering this service to you in the field, and we very often just bolt straight onto existing wireline or coil tubing companies' infrastructure that you may have there already. So if you've got coil on site, whether it's regular coil, we'll run in memory mode. If you have real-time coil tubing, then we'll have an option that will sit onto that, and you'll get the images and the measurements in real time from it there and then, which is a fantastic way to work. So a really good combination of the two technologies.
Okay, hopefully that answers your question, Rick. If anyone else has anything, please fire them across. I see Rick's asked another question. Is it the same tool for both applications, Tobben?
Yes, thanks, Rick. Pretty much, yes. Again, the main difference when we move from E-line to coiled tubing for E-coil is we will potentially run a flushing sleeve over the top of the camera system. It's optional. We can simply connect on and run with a bare camera system. But yeah, it's the same tool, multifunctional. The great thing about having the shroud, though, which comes with the kit, is it allows us to circulate clean fluids down the coil and deliver them right to the end of the camera. So if we're in an environment that maybe isn't perfectly clear, it could be turbid water, or it could be that there's oil there, you can circulate through the coil tubing, clean up the area of interest, and get a picture there. So it's a very simple operation for us. In the land environment, it's a guy with a truck with a pack of kit. We turn up and we utilize the best tools to fit the situation. Great, we're getting some good feedback on the chat window there, so that's really good to hear. Yeah.
Okay, we've got a question here from Clifford. When a camera is used with something like an overshot, would it be possible to use a memory camera too?
Yes, great question, Clifford. And in fact, the prototype that we've built for the real-time video whilst fishing using the overshot, it is a memory camera that we did at phase 1. Phase 2, we've looked at and made some designs already for a real-time version of it. But initially, we figured that perhaps the most common scenario will be regular conventional coiled tubing and trying to minimize the additional cost of bringing in anything else. So we bolt on memory camera with its own integral battery pack, and we can see the video footage at surface at the end of that first run. So yeah, it's a very non-invasive way of working. We don't have to change anything at the well site. We just bolt straight on to the existing coil.
Okay, and question here from Rick. So what happens when you engage the fish, but it won't come free, and you may have to disconnect your fishing BHA?
Yeah, great question. It is something we thought about in the design. We knew that this is one of the likely circumstances and potential risks. So we actually have a ball-activated release mechanism. So if you latch onto the fish, but you can't pull free, you pump a ball. That engages a release mechanism, and you actually pull out of hole, bringing the camera with you, but leaving a fish neck behind that you might be able to go in with perhaps a more heavy-duty approach. It has a profile on the outside and a clean bore down the center. So whether you choose to go in with another overshot or a spear down the center, you've got both options. But the key thing is we come back out of there with the video camera. So even as we're extracting it from the release mechanism, we can see what's gone on, and you can even then see the condition of the dressed fish that you've left behind. So we felt that was important. We thought that was a useful step. It also means we reduce potentially any lost in hole issues because we get the equipment back out. But critically, we've not made it any worse. If anything, we've left a slightly easier fish for you to go and grab.
One here from Rick asking, in coil operations, how does the camera stand up to some of the extended reach tools?
I'm not sure I fully understand that. I'm guessing that we might be talking about agitators here. Rick, do you want to just expand on that?
Yeah, that's exactly it. With some of these newer tools like the anti-friction tools and the vibration and getting deeper wells, we're using a lot of heavy agitators. So I'm just kind of curious how strong it is.
No, great question. And I'm actually going to be a bit cheeky here, and I'm joined by a number of colleagues from our operations and sales teams. And Pat, I'm going to pick on you because you've been an excellent source of information in the last few webinars. You're probably closer to this than I am. You've been in the field running these on-call jobs. So from your experience, what's the situation there, and what would you advise to Rick? Maybe I caught Pat off guard. The answer, Rick, is we have very robust cameras, and we put them through a range of vibration tests, and it is something that we design in through our manufacturing process, that they are able to withstand force, whether it's vibration or shock forces. They're very, very tough in those regards. And for our most advanced camera system that we're using at the moment, that we call Optus Infinity, which is a 360-degree array camera, we are regularly using that on very long reach laterals to measure perforations post-frac. And a number of those jobs are reliant on having agitators in the tool string to get to the toe of the well. So I don't think from anything I've seen, we've suffered from any mechanical failures from those types of devices. And if anyone else from the EV team wants to chime in from their own personal experience, that'd be great.
Yeah, Jeremy and Patrick had showed me that in Calgary when they had their little the SPE conference a little while back, but I haven't actually seen it out in the field, so I was kind of curious to see. But I know they were getting a lot more field testing. I just haven't seen it myself. So thanks for that.
Great.
We've tested and run the Spectrum tools with Halliburton using agitators before, and we've never seen any issues with them. So this is a service that we have used before.
How does the Halliburton tool compare to NOVs and to Tempest? Because pretty much from what I've seen, that Tempest tool is the most violent one out in the market, and a lot of people love it, but it's beating up a lot of equipment.
Yeah, I mean, it really depends on the vibration rates and current, but we can test with any tool. But at the moment, we've tested with a couple, and they've all came out fine in the end, and we've used on a few jobs before.
That's awesome. Thanks, guys.
Great. Thanks, Rick. Thanks for the questions. That's been great.